Hey everybody, Mr. Glover here. Just about to start our next set of notes. So the topic on today is going to be on combinations. It's a lot like a permutation, but with combinations, the order is not important anymore. So you'll see as we go through the notes today that it changes the possible number of outcomes. So start with permutations. So recall that permutation is a way to arrange a set of objects where the order matters. For example, if you have the letters A, B, C, D, then you can arrange that in 4 factorial ways, or you could arrange that in 4p4 ways. But what if we don't care about the order? What if it's something, words aren't a great example of this because the words do matter. What if it's something like combinations that you get in a bag of M&Ms? So number of red versus blue M&Ms. The order that they fill the bag makes no difference because when you shake it up, they still are in the bag. What matters is how many reds and how many blues. So in some cases, the actual order of the numbers or the letters or the objects doesn't actually matter. And that's really what a combination is all about. So let's do an example about this. Shanae is a real bookworm. She plans to start 3 book series over the summer. She's narrowed her selections down to Harry Potter, Hunger Games, Game of Thrones, Goosebumps, and Captain Underpants. Because she is only starting each series, it does not matter which one she chooses to read or which order she chooses to read the books. List all possible combinations of 3 books that Shanae can read. So basically, she's going to choose to start 3 book series. Doesn't matter when she starts them. She just wants to choose 3 of them. We need to figure out how many different combinations she could make. So instead of writing all these out, I'm going to assign a letter or a number to each one of these books. So Harry Potter, I guess we can call it book 1. Hunger Games 2, Game of Thrones 3, Goosebumps 4, and Captain Underpants will be 5. Okay. If we actually want to list all the combinations, we're going to have to kind of exhaust our list. So let's go through all the combinations that start with a 1. You could start with 1, 2, 3. You could have 1, 2, 4. You could have 1, 2, 5. You could have 1, 3, 4. Or 1, 3, 5. Or 1, 4, 5. And those are all the combinations that include a 1. The 1 technically is at the start, but it could be anywhere in the order. That's why we're not writing more than 6 of these, because we could have like 2, 1, 3, 3, 1, 2, 3, 2, 1. Those are all the same. It's all just 1, 2, and 3. All of the ones with 2. So you could have 2, 3, 4. You could have 2, 3, 5. Or you could have 2, 4, 5. And then lastly, if you don't have a 1 or a 2, the only combination that's left is 3, 4, and 5. So if we count all these up, this leaves us with 10 combinations. Which is a lot less than what we would get if we were working with permutations. There's many, many more. If you did 5 permutation 3, you would have had 60 combinations. So a list of objects in which the order doesn't matter is known as a combination. Notice that a combination AB has 2 factorial or 2 permutations, AB and BA. But both have the same 2 elements in them. They're the same combination. Remember that permutations were defined as NPR equals n factorial over n minus r factorial. And if there are R factorial permutations for a combination with R elements, we can define combinations and choose R, or in combination R, I guess, and PR over R factorial. So essentially, a combination is just a permutation, except you're also dividing by the number of ways you could arrange the objects. So in terms of a formula, n choose R is n factorial over R factorial times n minus R factorial. And this is the formula that we're going to use from here on out. It is on your calculator. It's in the math menu, just like the permutations are. You go math, probability, and then down to 3 for NCR instead of 2 for NPR. So now that we've got this tool, we really have to ask ourselves, does the order matter in the problem? Today, the order is not going to matter, but in the future, you might have a mix of problems where some of them are permutation problems and some of them are combination problems. So, example, there's 10 members of the grad executive. How many ways can you choose a president, vice president, and treasurer? Well, we have 10 members of the grad exec, so n equals 10. We are choosing 3 members, the president, vice president, treasurer, so R equals 3. Does the order matter here? Well, in this case, yes, actually it does. If you choose the first person as the president, and the second person as the vice president, and the third person as the treasurer, well then that's different than if you pick 3, 2, 1 or 2, 1, 3. So the order here matters. Order matters. What that tells me is that this is a permutation problem. Solving this, it would be 10p3. We're picking 3 from 10, which is going to lead us to 720 permutations. The next problem, though, is going to have the same numbers, but it's not a permutation issue. So 3 members to pick up grad gowns. Doesn't matter who you send in what order or how you select them, they're all going to pick up grad gowns. N is still 10, R is still 3, but this time the order doesn't matter. And what that tells me is that this is a combination problem. So it's very similar. It's going to be 10 choose 3 this time, or 10 C3. And that's only going to be 120 combinations. You should always expect that a combination will yield less results than a permutation because you're repeating things with a permutation. You can have the same elements in a different order and it's counted 2 or 3 or 4 or 5 times with a permutation, where with the combo, you just have those elements. That's it. It's like you take 4 letters. Those 4 letters are one combination, but you can make many words out of 4 letters, so there's many permutations. All right, so there's 12 girls and 18 boys in a pre-calc 12 class. The principal wishes to meet with a group of 5 students to discuss grad. How many selections are possible? So let's kind of pull some information out of this. We've got 12 girls, 18 boys. So in the total class, we have 30 students. At this point, we don't care whether they're girls or boys, they're just students. We're also choosing 5 of them to discuss grad, so R equals 5. And the question is, does order matter? In this case, order doesn't matter. So this is a combination problem. 30 students to choose from, and we're choosing 5 of them. 30 choose 5 is 142,506 combinations. All right, question B. How many selections are possible if the group consists of 2 girls and 3 boys? So now this is getting a little bit trickier. We can't just use a population of 30. We've got to split this up into the population we're pulling from. So we've got to basically break this problem down into 2 categories. We've got to break it down into the boys and the girls. And we have to treat it almost like a fundamental counting principle problem. We have to figure out the number of ways we can arrange the boys, number of ways we can arrange the girls, and then multiply them together. For boys, there was 18 of them, and we're choosing 3. So 18 choose 3 is the number of combinations of boys. The girls, there was only 12 of them, and we're choosing 2 of them. So 12 choose 2 is the number of combinations of girls. 12 choose 2 is 66, while 18 choose 3 is 816. So if we go and we multiply these together, there's 53,856 different ways that you could pick these students. Question C is similar, but with question C, we've got a third criteria. So we've got the girls, the boys, and we've got Zena. So if the principal demands that her daughter Zena must be one of the 2 girls, how many 5-member selections are possible? Okay, so in this case, we have to break it into 3 categories. First category will be the boys. Second category will be the girl that's not Zena, so just 1 girl. Third category is Zena. So out of the boys, we are picking 3 of them. So 18 choose 3 is the number of ways we can pick the boys. We're only choosing 1 girl out of the pool. We used to have 12 girls in the class, but we're going to pull Zena out of that category. So now there's only 11 other girls in the class. So we are going to choose 1 out of the 11. 11 choose 1 is the number of ways we could pick that other girl. And Zena, there's only 1 of her. 1 choose 1 is the number of ways we could pick Zena. So if we crunch the numbers on this, 1 choose 1 gives us 1 way to pick Zena. 11 choose 1 gives us 11 ways to pick 1 other girl. And 18 choose 3 is still 816 ways to pick the boys. If we multiply these together, we get 8,976 ways to pick. Compared to our 53,000 from before, it's a lot lower because we have less people to choose and we have more specific criteria. So usually the more specific something is, the more the less combinations you'll get. And the more broad the criteria, the more ways something can be done. So let's try the problem that's probably been on your minds at some point in time, and it's Lotto 649. We're going to actually use combinatorics to figure out how many Lotto 649 combinations there actually are. So the way that Lotto 649 works is that you're choosing 6 numbers from 49 numbers. You have 49 to pick from, basically like a big bin full of balls with numbers written on them, and then 6 of them get selected. The order that they get picked in does not matter, but if your numbers get chosen, then you win. So essentially, Lotto 649 is 49 choose 6. There's so many ways you can do it. Turns out it's a lot of ways. With 49 numbers, if you choose 6 of them, that leaves you with 13,983,816 different combinations. So the question everybody always wants to know, what's the probability that you'll win the lottery? Well, there's only one combination that's going to win, and there's 13,983,816 of them. So the probability, P, is going to be 1 divided by 13,983,816, which is an extremely small number. 1 over 13,983,816. Well, that gives us 7.15 times 10 to the minus 8. Multiply by 100. That gives us a 0.00007% chance. So your odds are 1 in 13, almost 14 million, and your probability is 0.00007%. Incredibly low odds, which I think most people know. All right. In most poker games, 5 cards are randomly dealt from a deck of 52. So we can use combinations to actually figure out statistics on things like how many ways can I get a royal flush, or how many different pairs are there. So if you've got a deck of 52 cards, we know that n equals 52 for the whole deck. How many hands are possible if you're picking 5? Well, it's just going to be 52, choose 5. I should probably write that the order doesn't matter, because you can just rearrange your cards in your own hand. 52 choose 5 is 2,598,960 possible hands. But as soon as we start applying criteria to this, you'll see that the number of hands that match the criteria are nearly 2,500,000. So how many hands have 5 hearts? Well, we have to now only dip into the pool of hearts. If there's 52 cards, that's 13 of every suit. So there's 13 hearts in a deck. So if we're picking a hand with 5 hearts, well, we're now down to 13 choose 5. We're choosing 5 out of 13. That's only 12,000 or 1,287 hands, which is far fewer than our 2 million possible total hands. So that means that the chance of getting a flush with hearts is actually quite low. You have to take this number of hands and divide by the total number of hands to figure out your probability. How many hands have 4 hearts and 1 spade? Well, we have 13 hearts in the deck, and we also have 13 spades in the deck. So if we want to figure out the hands that have the combination of 4 hearts and 1 spade, we have to break this apart into 4 hearts and into 1 spade. If we have 13 of each suit, the way to get 4 hearts is there's 13 and choose 4 ways to do that. And the number of ways to get 1 spade is going to be 13, choose 1. This is going to work out to 9,295 hands. How many hands have exactly 3 hearts? So if we have exactly 3 hearts, that means that we can have 3 hearts and we can have 2 other. And the 2 other can be anything. So we have to think about what pool of numbers do we, or what pool of cards are we pulling out of? We've got 13 hearts. There's 52 cards in the deck. That leaves us with 39 other. So the way to get 3 hearts, or the number of ways to get 3 hearts, is 13, choose 3. And the number of ways to get 2 other is 39, choose 2. If you multiply these together, you will end up with 211,926 hands. All right, and one more of these card problems. How many hands have at least 3 hearts? So this slight change in wording makes all the difference in our problem. At least completely changes the question. because we have to now split this into cases. We have to think about how many hands have 3 hearts, how many hands have 4 hearts, and how many hands have 5 hearts. So we have to do 3 separate calculations. So we've got the 3 hearts and the 2 other. We have to add the other combinations. So we could have 4 hearts and 1 other. Or we could have 5 hearts total. So these are our 3 cases, if you will. Case 1 of 3 hearts, case 2 of 4 hearts, case 3 of 5 hearts. So the first example, 3 hearts and 2 other, we would have 13 choose 3 ways to pick our hearts. We would have 39 choose 2 ways to pick our other. 4 hearts, we would have 13 choose 4 ways to pick the hearts, and we would have 39 choose 1 way to pick the other. And then in the last case, 5 hearts, we would have 13 choose 5 ways to pick those. So we have to multiply all of these together. 13 choose 3 times 39 choose 2 is 211,926. We got that from before. 13 choose 4 times 39 choose 1 is 27,885. And 13 choose 5 is 1,287. If we add all of those up, we have a possible 241,098 hands that meet our criteria. So this is going to be the harder type of question because we have to use cases. All right, we're almost done. We can use different notation to write and choose R. So some people, well, mathematicians typically like to try to minimize how much they write, and they try to make things as concise as possible. So instead of actually writing out this N choose R formula, and instead of even writing out NCR, you can just write the brackets with N on the top and R on the bottom. It's kind of a lazy way to write it, but it's equivalent to N choose R. So fundraising committee is to be broken from a group of 8 students. How many ways can 5 students be chosen? Well, we have N equals 8. We have R equals 5 being chosen. The order does not matter. Order does not matter. And so essentially we're choosing 5 from 8. It's 8. Choose 5, except it's going to be written this way this time. That's going to equal 8 factorial over 5 factorial times 8 minus 5 factorial, which is going to equal 56 ways. How many ways can a committee of 3 students be chosen? Again, same idea. N equals 8. This time R equals 3. So we're doing 8 choose 3, which is 8 factorial over 5 factorial, or sorry, over 3 factorial times 8 minus 3 factorial, which again works out to 56 ways. Just kind of surprising. These are the same number of ways. Notice that the number of ways of picking R objects from a set of N objects is the same as not choosing R objects from N objects. Or in other words, N choose R is equal to n, choose n minus r, as long as n is greater than or equal to 1. So basically, number of ways of picking 3 things is the same number as the way of not picking 3 things. So if you had 8 people and you chose 3, that's the same as choosing 5, because 5 is the equivalent to not picking 3. It's kind of weird and it's kind of a strange way to think about it, but because of the way the formula works out, both formulas are going to simplify to 8 factorial over 5 factorial times 3 factorial. It's just whether it's 5 factorial times 3 factorial or 3 factorial times 5 factorial. So this is a little bit of a trick. You won't need to use it a lot, but sometimes it will save you the math if you already know one of your answers. So that's where we're going to end things today. I've got some problems for you in your textbook. I should probably write that text. But, number 1, 3 to 7, 11, and 13. This will be your homework for next week, and that's pretty much it. So hope everybody has a great weekend. I will see you all on Monday, and if you've got any questions, just don't hesitate to let me know. Send me an email, or bring it to the Zoom session, and we can discuss it on Monday. All right, I'm going to end things. Take care, and talk to you all later.